title of our talk is Utility of Lava Tubes on Other Worlds. First, I'd like to acknowledge my co-authors, Thomas L. Billings here, Cheryl Lynn York, my wife, who's helping here today. She likes to say she's playing Vanna White. All three of us are from Oregon L5 Society. Planetary geologist Stephen Gillette with the University of Nevada, and Century West geotechnical engineer Mark Herbert. Some of this work was made possible by a contract from NASA's Office of Exploration.
In one incarnation or another.
Yeah. Could you use 160 million cubic meters of open space on the moon, shielded by 40 meters of basalt, with a constant temperature and free of lunar dust? Have I got a site for you? In fact, several. For an amount of Good. No, I'm waiting for you.
Oh, okay, well, sorry.
Yep, there we go. For an amount of excavation similar to that required for a surface habitat, and perhaps much less, we can gain access to large lunar or Martian lava tube caverns. The one shown here is 90 meters in diameter, which is only medium-sized for the moon, and it's also a possible size for Mars. For scale, we show a typical Shuttle Bay class module used in current plans. Okay.
Is that the little red thing?
The red thing circles the little,
Okay.
the little black spot.
Inside the red.
Yeah.
Our favorite moon bat.
Incidentally, I apologize for the quality here. It looks like the Fresnel lens inside the overhead has partly fallen in, so it's giving us bad light. Today we'll explore the shapes and uses of lava tube caves using a variety of examples from Earth. Lunar lava tubes can be 10 to 15 times larger than these, while Mars caves can be 3 to 4 times larger. Okay. Sinuous rills are frequently the collapsed trenches of drained lava rivers. Where the trench disappears, the areas between the green spots here, we often find caves. We often find the channel continues as a lava tube cave. Each segment is considered a unit cave, while the whole set is sometimes called a cave system. As you see here, caves, 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 caves. This is all one flow. Okay. We have several ways to locate lava tubes, which we discussed in our paper, Lunar Lava Tube Sensing, in 1992. On the moon, sinuous rills often appear near the Mare Highland boundary. On Mars, as on Earth, they are associated with large shield volcanoes. We will assume for purposes of this discussion that these rills do lead to lava tubes. These arrows point to 2 of the lava tubes identified in that Combs and Hawk study, that listing we showed you at the beginning. Usually we think of singular long lava tubes, but there are other varieties of lava tube caves. Where the underlying slope approaches 0 degrees, the lava channel will brachiate like a river delta, forming complex anastomosing caves. These caves might be preferable for habitation because they're so different and interesting, containing a variety of rooms and passages. Now, these large globs are the open areas to the surface, and then these long lines represent the undersurface cave areas. As you see, they can get kind of complicated here and there. Thank you. Some lava tubes develop vertically with passages on several levels. Such vertical development can be useful for gravity-fed processes. So you have a level up here, which they're counting apparently as part of the same cave system, and on down and down and down. And these represent some lava bridges between levels. Here we have a typical cross-section. Don't expect to find a cave that contains exactly this appearance, but it illustrates some of the things that we look for in caves. First, the tumulus is quite often found. It's an area where overflows have gone up on the surface, and it makes a slight ridge over the cave area. Inside the cave, we find flow marks, or flow horizons, or bathtub rings left by subsequent lava flows. That's as high as they got, and then they went down again. Afterwards, they leave behind cave linings, which is a thin layer of lava deposited on the cool cave wall, relatively cool cave wall by these flows. Another thing that can happen is a very hot flow, probably from deeper within the magma chamber, will come out after the first flows. And these flows will eat away the lava that's already in the cave, and even eat down into the bedrock underneath the cave. And that tends to form a bench formation where you have an old floor level, so it's like on a level on top, and then a trench in the middle where it goes down deeper. We can use features like these. The floors of lava tubes can take various forms. I'm going to start on the right here, plain, because that's what we usually desire the most. You can also do trench, which is the same thing as saying we have these benches on each side. Sometimes the last lava flow will go through and drain, and the floor, which is really the ceiling of the inner lava flow, will collapse underneath there, and you get this deflated thing, kind of like that cave we showed you early in the other show where the whole surface just kind of dipped. Other times, there'll be a surge that will inflate the relatively soft floor of the lava tube, which is really, again, the top of the last flow, and cause a big ridge to form in the middle. Occasionally, we'll find even a smaller lava tube inside the lava tube that way. We also want to mention any of these floor patterns can have rocks on top of them, breakdown rocks, so that can be a problem. Ceiling linings, sometimes the later flow will actually fill up the cave, in which case you'll get a coating, an extra coating on your ceilings, and you can tell that it's smoothed over an area that had been a rock fall up above and things like that. You'll also get what we call lava sickles from remelt, and we'll have a picture of that a little later. And as we pointed out in the earlier show, you can find places in the ceilings where there has been breakdown, and that just increases the interior size of the cave in the top to create a breakdown dome. The other thing I want to mention is that the end of the cave is not always the end of the cave. When you're dealing with a liquid medium forming the cave, you can often have a siphon, for example, an inverted siphon, where the last flow gets stopped. I hate to use this, but it's just like the bottom of your toilet. And you'll find as you're exploring this cave, you come to the end, the ceiling comes down to meet the floor, and it just pinches out. And here you were in a huge cave bigger than this room just a moment before. You know, it doesn't make sense that this would be the end of it. Well, it's not. If you can manage to get a little further along, you'll probably find a whole other cave the same size as you just left. A breakdown pile can also cause the end of a cave. There'll be a breakdown in which lava will pile up behind it. Very often, that lava will erode an area in the ceiling and even pop out the top and create a skylight opening that you can use later. And we have many caves like that. Okay, thank you. Oh, next slide. Oh, that is the end of over here. Okay. Thank you, and we need to swap over to our slides now. Any questions while they're making transition? We do have time for questions in the middle of this, as it turns out.
How would you verify the structural integrity of the lava tube as you cited it?
Our main mechanism of verifying structural integrity at this time is the fact that it exists. On the moon, the period of lava tube formation is long over by about 3.8 billion years. If that lava tube is there, it's a survivor. It has survived 3.8 billion years. But there are ways to test it, and we did a drill core of a lava tube in Oregon as part of our NASA study, and that was Mark Herbert's geotechnical work. And we'll be talking about that in the second half of some of his findings about how strong a lava tube cave is and what you can do to make it stronger if you need to. But it's quite strong all by itself, partly because of its natural arch shape. That gives it additional strength. How are we set for focus?
Good.
All right.
Could you turn the lights down low?
So now we're going to go into some practical and maybe a few impractical lava tube caves. And normally, I want to mention that we normally follow safety recommendations of the National Speleological Society, the other NSS who had the initials before we did. So respect them. And that includes wearing hard hats for safety and at least 2 sources of light apiece, and traveling with more than 1 person. As someone was explaining to us earlier, they like to follow the rule of 3s. Tell 3 people where you're going, have 3 people along, and carry 3 sources of light apiece. If you ever get caught deep in a cave and your light goes out, you won't mind carrying a little extra light with you, believe me. Anyway, look at these caves that we'll be showing you with an eye to how you would use their features to help you on the moon and Mars. No one has yet explored a lava tube on the moon. But we have visited Hadley Rill, a lava channel on the moon. Hadley Rill is one of the largest examples of a sinuous rill. We have sinuous rills here on Earth, too. Remember that large crater I told you about? That, I think, was in this picture, maybe right up here, yes. And coming out of that is a long, long, sinuous rill. This, incidentally, is a cone-shaped cinder cone. It comes up out of the picture. Not in view. This is at Lava Beds National Monument in Northern California. As we get closer to that rill, and in fact this was taken from the top of that butte I was just talking about, we can see typical collapsed trenches and deep rimless craters in a snaking line. It's a trench, a crater, crater. At the end of that rill is a dark hole. Again, our standard researcher for reference here. Co-author Tom Billings is the man in red on the right edge. As we draw near, the ground drops away to reveal one of the largest terrestrial lava tubes, California's Skull Cave at Lava Beds National Monument, almost 30 meters in diameter. The entrance is full of collapsed debris that must be negotiated. It would take about the same amount of work to make this entrance navigable as it takes to cover a surface habitat. If the debris has turned into fine regolith, it may be used to cover a surface habitat. In return, we are granted access to a large, sheltered volume for any use. Note my colleague, Mr. Billings, standing in his blue jumpsuit over against the far wall for scale. In case you're having a little trouble finding him, he's right there.
Draw the laser pointer in again.
Oh, yeah.
Yeah, right down. Excellent.
Secret laser pointer. Thank you, Darth, wherever you are. Here at Oregon's Lava River Cave, we see the layers of basalt flow that protect the cave from the outside environment. Where the breakdown is a problem, we might use cable cars made from indigenous glass and metal, or suspend a transportation system, or even an entire base from the arched ceiling. Some entrances may be easy walking passage. Another way to enter a lava tube is through the roof. In advanced bases, we may drop in a prefabricated elevator platform to lower base elements or spacecraft themselves down to the level of the tube. Smaller skylight entrances would be ideal for personnel and small supplies. Even very small openings could be used to run light pipes, power, and communication lines. Of course, you can drill or blast an entrance wherever you like, and I'd just like to give a nod to my brother, Kyle, there, who climbed down into a little lava tube and poked his head out in this picture. Floors of lava tube caves can consist of frozen ponds of black lava with a smooth and level surface. Such bedrock surfaces are rare on the lunar surface, and they can be valuable for anchoring heavy machinery or fixing production lines. It's my brother and my father in that picture. Let you know. In other areas, the lava flows downhill in frozen motion, making natural ramps. On Earth, and possibly on Mars, sand washed into a cave can form a smooth, virtually level floor. Since this mechanism does not exist on the Moon, we expect large areas of lunar lava tubes to be free of troublesome moon dust. Sand can also wash in through cracks in the basalt flow. These cracks, although they intersect the cave, do not appear to weaken it. As an integral part of the basalt flow, these caves are almost indestructible. Slightly cooler lava develops cracks in its smooth floor. We also get a view here on the ceiling of lava sickles. These small stalactites are thought to form when hot gases of a later flow cause solidified lava to remelt and drip. Once cooled, they will grow no further. A later flow can dig a channel in the floor, deepening a cave. The final flow may break up as it cools to form a rough, knobby texture. We also see flow marks, or so-called bathtub rings, on the walls here. It appears that most breakdown occurs in a lava tube cave when the lava flow is withdrawn and areas incapable of self-support collapse. Once cooled and settled, lava tubes appear very stable. Forest Service geologists observed no changes in Washington's Ape Cave on the south slopes of Mount St. Helens, even after its numerous earthquakes and eruptions, including one that blew the north face away. We have reports from people caught in Hawaiian lava tubes during earthquakes. One found no damage. Another heard a single stone fall that they had noticed earlier appeared loose. Here we see several features. A smooth lava bench down on the lower left, about 25 centimeters above a smooth, sandy floor with a breakdown pile in the rear. We have a different standard researcher there for scale, that's me. Breakdown stones are typically blocky and may be useful for construction, ballast, counterweights, and maybe even paving. Parallel cave walls can be useful as support for bracing. If you look closely, you'll see the roof is not complete overhead. Above it is a larger cavern. A base could be built on beams laid across this open ceiling, while the lower passage we see here could be used for transportation and utilities. The slight slope of the lava tube can help move fluids along by gravity. The hydraulically formed arched roof of a lava tube can be very strong. Co-author Mark Herbert, a geotechnical engineer with Century West in Bend, Oregon, analyzed cores taken through a lava tube roof as part of a NASA study we conducted. He found a 3.5 meter thick roof could support 45,835 kilograms per meter on Earth. Assuming similar basalt strengths, and lunar basalt might be stronger due to its anhydrous glass content, this translates to 137,000 kilograms per meter on Mars and 275,000 kilograms per meter on the Moon. He also states a thicker roof would be able to support substantially more, and weaker roofs could be strengthened with rock bolts. Incidentally, at this point in Lava River Cave in Oregon, heavily traveled U.S. Highway 97 crosses directly overhead. Just briefly, here are a few unusual shapes found in lava tubes, such as this teardrop-shaped passage, this unusual lava wall or rampart, and this natural lava bridge over a lower cavern within a cavern. One last thing I have to mention is ice. On Earth, cold air can be trapped in the insulating basalt cave. Water flowing or dripping into the cave can freeze in beautiful formations, or it can flow into a sump where it adds to a frozen lake layer by layer. You can see, since a ramp was built to this lake, the ice has risen nearly to handrail height. Since this is heavily visited, those fallen rocks on top of the ice may not have occurred naturally. These frozen pools may exist on Mars, giving valuable clues to past climate and atmosphere. On the Moon, cometary volatiles may have condensed and frozen in sheltered lava tubes. In either place, it would be an important resource. From our lunar lava tube-based simulations with young astronauts and their families as crew, our research team learned many things. The trouble with volcanic dust, the need for entertainment in the still, dark lava tube environment, the speed and ease of construction in a sheltered place. And don't underestimate the psychological advantage of knowing you're protected by the thick, strong basalt roof. A base can commence productive operations more quickly than on the surface. Work may be made easier and faster by using lighter, more flexible spacesuits, and risk hazards and costs are significantly reduced over surface operations. Maintenance is also easier when infrastructure can be left in the open. Constant temperature and lack of dust will simplify environmental controls, reduce wear and tear on equipment, and possibly improve health. If we're very lucky, we might find a sizable lava tube with an easy walk-in or drive-in entrance. Inside, we might find a smooth, flat floor, handy parallel bench formations, and a clean, arched roof. It could happen. All we would need to do is move in. They're waiting for us. Thank you. We have maybe a minute or two for any questions further. Okay. Thank you very much.
Order and everything, right?
Any of you come out to Oregon, give us a buzz. We'll take you out to a lava tube.